Hi, I'm Darshan, a field engineer at One Energy. Welcome to today's Science Shot. Buckle up. Today we're going to give you a crash course on momentum. Before we begin, we ask you to review Ethan's Science Shot about energy, as some of those concepts will pop up here too. We've talked a lot about forces in our previous episodes. Remember, to make an object move or to put an object into motion, a force must be applied to it. But can we measure the amount of motion an object has? Yes, that's momentum. So momentum is a measure of how much motion an object has when a force is applied to it. An object that is moving has momentum. The amount of momentum an object has depends on two variables: how fast that object is moving and how much that object weighs. The way we can represent momentum is with this equation. Momentum, shown here as the variable p, is directly related to the mass or the weight of the object and the velocity or the speed of the object. If an object has a larger mass or a larger velocity, it will also have a larger momentum. But if the object is still and is not moving, its velocity will be zero. And based on this equation, the momentum will be zero. So in order for an object to have momentum, it must have both a non-zero mass and velocity. Momentum, just like energy, is always conserved in a closed system. That means momentum can never be created or destroyed, only changed or transferred. For example, when you have two objects that collide with each other, each with their own value of momentum, the total momentum after the collision is equal to the momentum of each of those objects before the collision. With this in mind, we can create another momentum relationship equation like this. Remember that each side of this equation is the calculation for momentum. So we just set the momentums of two objects equal to one another to show that the momentum is conserved. Let's illustrate this concept with a real-world application of momentum: toy car collisions. In our first example, the red car is parked and we're going to launch the blue car into it. Before the collision, the blue car has a higher momentum because it's moving and has a velocity, while the red car has no momentum because it isn't moving and does not have any velocity. When the collision occurs, there is an exchange of energies from the blue car to the red car, resulting in a change of momentum between the two. The blue car now has lower momentum than it did before the collision because it transferred some of its momentum to the red car. In this next example, we'll have both cars moving at the same speed before they collide with each other. Both the red car and the blue car have the same momentum and are moving towards each other. When they collide, the momentum change is equal, but the cars react in opposite directions. The cars change direction and move backwards at the same speed after the collision. And finally, with our last example, the same cars are going to collide, but the red car is moving much slower than the blue car before the crash. The red car has a lower momentum than the blue car coming into the collision. The total momentum will remain conserved, but the collision will allow for a transfer of some momentum from one car to the other. The blue car slows down while the red car speeds up after the collision. This is because we are conserving the momentum, and momentum is being transferred from the blue car to the red car. These three car collisions are just a few examples of how momentum works. Remember, momentum is a measure of how much motion an object has when a force is applied to it. Can you think of any other examples of momentum in your life? Thanks for watching this installment of Science Shots. Be sure to subscribe to our YouTube channel to catch the next episode. And remember, challenge everything.